Okay, now that we've covered tables and we've covered relations between tables in relational databases, what have we left out? In this last final short video, before we get into actual bioinformatics databases, I want to introduce other kinds of databases, kinds that don't use SQL. So before we start, let's just review something that I mentioned, but we didn't really describe, which is something called a database schema. I used the term, but I didn't really say what it was. So a schema defines exactly what data structures can be present in a database. In the case of relational databases, it defines the tables and it defines the relationships between those tables. And that's all. If you have data that doesn't fit into those tables, or if you have data that doesn't fit into those relations, then you can't use that schema, or you have to modify the schema to accommodate it. That introduces some constraints that can sometimes be very frustrating. Tables, as we've seen, they're rectangular. So let's just remind ourselves what that means. We have one entity gets represented in one table. We have one row in that table that represents a single record. And we have one field, which is one entry in that row, one column within that row, is represented a single property or a single attribute of a single record of that entity. But there may be occasions where we don't know all the fields in advance, or we might have to define so many fields that most of the fields would be empty most of the time. This makes these kinds of rectangular representations of data somewhat constraining. What happens when we need more flexibility? What happens when we don't know all the fields in advance? Or maybe we have an idea of all the fields in advance, but we only expect to use a few for any given record. So most of the fields will be empty most of the time. We'll make this huge table and it won't contain very much. So here's an example. A person might visit a doctor and they maybe present some symptoms, and then they're assigned or prescribed some treatment. How do you represent that in a table, considering there's this vast range of things that they could be coming with, and they could be treated with any number of options? Well, one way to do it is an extremely flexible way. And you can think of this as basically a table with only three columns. One column is the entity name itself, another column is an attribute, and the third column is the value within that attribute. Those are the same things we have in a table in a relational database, but we haven't organized it all ahead of time into tables. So it allows an unlimited number of attributes because we can just keep adding names, entries in that second column. So here we have an example of this. Here's a patient who visits, this is quite some time ago, this is from Wikipedia. So here's the first field is in the in between these angle brackets. So we have patient XYZ visits in 1998 at 9:30 a.m. That's the entity. It's a patient visit. The second is, in this case, temperature in degrees Fahrenheit, 102. That's maybe 38.5. So there you have the entity, the patient visit, the attribute, which is their temperature, and the value, which is degrees. The second part of this, EAV triple in this, is the same entity, but it's a different attribute. In this case, they have a cough. The third, well, now they have a cough, so now another field is relevant. In this case, it's a type of cough, and it's with phlegm, and it's yellowish and streaks of blood. And finally, the last EAV triple that we have to consider in this is the same entity, now a different attribute, their heart rate in beats, and it's 98. So they come in with an elevated temperature, a phlegmy cough, and a heart rate of 98 beats per minute. So they're clearly suffering some form of infection. But you can see that by just using these three columns, you can define a whole lot. The EAV model, that triple store model, has an enormous amount of flexibility. The truth is, not all databases use tables, and not all databases use SQL. Some databases hold collections of documents, what they call documents, which are not rectangular. Popular versions of this include MongoDB, which I use a lot myself, CouchDB, which is meant to emphasize the laziness of being able to use it, and Neo4j, which is represented specifically graph kind of information. Some models use triples of information, such as the entity attribute value on the previous slide, and another related one called RDF. And some bioinformatics databases use some types of these models. One of the cool things about these is that you can use such a database. You can set up MongoDB today and drop some data into it without a schema at all. And it's still queryable. You can still get data from it and ask questions about it. You do not need any schema to do it. As long as the data as long as the data is well formed, you can drop data into it. So what is a document? That begs the question, what is a document? So it's a collection of data. Often it's nested data, and it's structured in some way so that a computer can read it. The common structures include XML and another structure called JSON. The example here on the right is a piece of data describing a student. And so here what we have is these curly braces define the limits of the document. Everything inside this first curly brace is the student. So we have here the tag, which is that it is a student. It could be a different type of document. The student's name is John, the student's class is intermediate, and then their address is further nested. So you can see these other curly braces indicate more nesting. And you could have, this outer curly braces suggest that you could have other types of entities represented in the same document. That's the basic idea of one of these things. And because it's anything that fits into this format can be deposited in such a database, there's enormous flexibility. You don't have to define a schema ahead of time, but sometimes you do. Okay, so strictly speaking, NoSQL databases don't have to use schemas. They don't require, the actual engines don't usually require a schema for data to be just dropped into the database. So long as the documents are valid, they can do that. However, schemas might be really useful in this case, just to make sure that the data is representing what you expect it to represent. If you're working with some software, for example, and transferring data between software components, you might want to be absolutely confident that the data has everything that it needs. And so in that case, you might use a schema to ensure it. That's also true. Recent versions of all Microsoft Office documents, they actually store documents in an XML-based format, and they use a defined XML schema to do it. So when you open Microsoft Word or PowerPoint, you're actually using an XML schema, and in fact, that document can be stored in a NoSQL database. Now, one way to think about this, just as an overall picture, is to look at it like this. You can say, oh, here we have an SQL database with these tables and the defined relations between these tables. You have to define the schema ahead of time. It gives you enormous power and an ability to predefine questions that you can ask of that data and get answers quickly. NoSQL can also be very fast, but here every one of these circles here represents a document. And these documents might be linked to other documents by having references to other documents within them. And so you can query such a database by just asking what documents have the properties that you're looking for, and then traverse the database by linking to other documents and so on. Now, that's where we are with this. Next, we're going to go into some bioinformatics databases, and for the most part, you won't be using the backend. You won't be worrying about whether the underlying database is a relational database or a NoSQL database or something else. But it's good to know that they're what they are so that you can use them if you want to. So Ensemble is an SQL database, and it exposes the SQL. You can use an SQL client to query it. The same is true with the UCSC genome browser, which is very popular. UniProt, which is a database that we'll look at for protein information, actually uses RDF. And NCBI, I think, internally uses a variety of ways of storage, but probably primarily relational databases. But for the user, if you want to do a lot of downloading, they offer a lot of flat file downloads and some specialized tools to do it. They do offer, in the flat files, they offer SQL flat file downloads of many types of data so that you can then use them in your own applications. So that's where I'm going to leave this very short video, and we'll come back to specific databases next time. See you then.